determine the absolute minimum and maximum values of the function f of xy equals 2x squared minus 2xy plus y squared minus y plus 3 on the closed triangular region with vertices 0, 0, 2, 0, and 0, 2. So we should probably give a quick sketch of that. We would probably give you the picture, but this one, I think we can draw the picture. Okay, so what do we have? We have the three vertices. 0, 0 would be here. 2, 0 would be here. And 0, 2 would be here. Oh, okay. All right. Cool. And so it's a triangle. So we mark the edges. And there you go. There's your triangle. Okay. Now I'm a little bit nervous. I copied the problem down wrong. But who cares? We can still do the problem. All right. Yes, did I get the right triangle? Yeah. Yeah. It looks right to me. Okay. Now, what kind of problem is this? One of the things that you have to learn when you're doing math and in general in life is saying, I'm faced with a problem. What type is it? Now, there's a few keywords in problems. Here, our keywords are absolute min and max. And whenever you see a problem that says, find the absolute min and max, that's the, okay, I'm going to make a list type problem. So, this one, we're going to form our list. Our list of potential points where a min or a max could occur. So we're going to make a list, and then after we made our list, we're going to check our list. But first, we make our list. Now the list, remember, that's where things could occur. And so to start off, you always start throwing into your list things which are easy. The easy things are the corners. So you add the corners to your list. 0, 0, 2, 0, 0, 2. Good. Corners are done. All right. Now, after you get your corners out of your way, so I suppose, where do you look? We should make a list of our list. Corners, interior, and boundary. I like to go in this order because corners are trivial, but you always want to make sure you have them. Interior is not usually too bad, because interior, that is where you set the gradient equals 0. Then boundary, it's not so bad, but lots of cases, usually. So if it's a triangle, there will be 3 cases. If it's a rectangle, 4, so forth and so on. So I sort of I prefer this order just because it's sort of easy to hard. Okay, so we take our gradient. So our gradient of our function would be 4x minus 2y, comma, negative 2x plus 2y minus 1. All right, and we're going to set each of these equal to 0. Now, from the first equation, we can see that we have the following. 4x minus 2y equals 0 tells us that y has to equal 2x. And now that we know that y equals 2x, we can go into our second equation, and we say that, well, minus 2x plus 2 times 2x minus 1 equals 0. And that becomes 2x equals 1. Because that'll be 4x minus 2x, and then 1 moves across, or x equals a half. Now, if x equals a half, y is twice x, which tells us that we're getting to the point 1/2, comma 1. Now, the question is, does that show up on our list? The answer? Well, you check. Where is 1/2, comma 1? Well, 1 would be roughly there, and a half would be roughly there. So 1/2, comma 1 would be at that point. And the thing we're checking is it on the inside? If it's on the inside, we include it. If it's on the boundary, we actually don't have to include it because we're going to do the boundary separately. And if it's on the outside, we definitely don't include it. But when it's on the inside, we include it on our list. So it's on our list. Okay. Now we go to our boundary. We have 3 sides. So we do each side. Let's start with the bottom side. What's true about the bottom side? Y equals 0. So, on the bottom side, our function becomes f of x comma 0. So, everywhere we see a y, we put a 0, which there's a lot of y's. That becomes 2x squared plus 3. Take the derivative of that, 4x equals 0. Or x equals 0, which means that we're at 0, 0. But that's already on our list. Good. All right. That side is done. Now, let's go to the right-hand side. Over here, what's true on this side? X equals 0. So y equals 0 is this part, x equals 0 is this part. So, this will become f of 0 comma y. Well, everywhere we see an x, you put a 0. So that's 0, that's 0. Y squared is y squared minus y plus 3. Take that derivative. 2y minus 1 equals 0. Now here, we get y equals a half. So that would correspond to the point 0, comma half. That's on the part of the boundary that's our interior. See, if we'd gotten a solution over here, would we care about that kind of point? No, of course we wouldn't care about that kind of point. That point is irrelevant to our problem. So 0, comma a half. All right, well, our last side, the slanted side. So we have to find something, a line, that goes from 0, 2 to 2, 0. Well, this line is not so hard to find because the slope is negative 1. And so that says minus x, and the y-intercept is 2, plus 2. So what we can do is for this line here, the slanted line, we can rewrite and say our function looks like f of x comma y is really f of x comma negative x plus 2. So one way that sometimes we think about doing this is thinking about parameterization. We're parameterizing our line. In this case, we're parameterizing it in terms of x. So here we go. Everywhere we see an x, there's an x, so that makes life easy. 2x squared minus 2x times y, which is negative x plus 2, plus y squared, negative x plus 2 squared, minus y plus 3. So this becomes 2x squared. Then if we distribute through, that'll be plus 2x squared minus 4x. Then over here, plus x squared minus 4x plus 4. Oops, this minus y, I shouldn't have written that. I should have written negative x plus 2. So plus x minus 2 plus 3. So what does that give us? 2x squared plus 2x squared plus x squared. That's 5x squared. So that takes care of the 2x squared, x squared. We have minus 4x plus x. So that is minus 7x. And then we have plus 4 plus 3 minus 2, which is minus 5. All right, so we get 5x squared minus 7x minus 5, which tells me this is definitely not the problem I thought it was, but that's okay. It's still a problem. Take the derivative. You get 10x minus 7 equals 0, or x equals 7/10, which says that if you came over here to 7/10, roughly right there. So this is at x equals 7/10, and then y equals whatever it turns out to be. Well, it's 2 minus 7/10, which would be y equals 13/10 if you were after that point precisely. Okay? So 7/10, comma 13/10. And now we're done with making our list. What comes next? So the next thing is we plug everything into our original function. And this is the part where you hope you don't see something like this. So, well, we did. All right, let's go through. 0, 0 is pretty easy. Get lots of zeros, then a 3. on the end. 2 comma 0. Well, 2 comma 0, if I actually come over here, it's pretty easy to plug in 2 comma 0. It's 2 times 4 plus 3. So that's 8 plus 3 is 11. 0 comma 2, I can come over here. That's 4 minus 2 plus 3. That's 5. 1/2 comma 1, well, have to do it here. 2 times 1/2 squared is 1/2. 2 times 1/2 times 1 is 1, so minus 1, plus 1 squared plus 1 minus 1 plus 3. Well, we get 2 plus 1/2. I'll say 2.5 or 5 halves, 2.5. All right. 0 comma 1/2. Well, we can plug it in here. That would be 1/2 squared, which is 1/4, minus 1/2 plus 3, which is what? Well, that's really 3 minus 1/4. That's 2.75, or I guess if you don't want to do it in that way, that's 11/4. And this is, by the way, 2.5. All right, 7/10, 13/10. Really? All right. Okay, we'll do it. 7 squared, 49. Double that, 98 over 100. Then 2 times 7 times 13. Well, that's 182 over 100. Now, you might be thinking to yourself, is it really 182? It is. But you also might be thinking to yourself, are we really going to have to do this? No, we put nicer ones on exams. Okay, y squared, 13 squared, 169 over 100. Y is 13 over 10. But we're going to write that as minus 130 over 100. And 3 is 300 over 100. So I'm just putting things over 100. All right, so let's see. What do we have going for us in the plus directory? We have 300 plus 98 is 398 plus 169. 398 plus 169. It's like 400 plus 167. So that's 567 over 100. Then we're going to subtract off 182 and 130. Well, if you combine those, that would combine to give you 312 over 100. So 567 minus 312, well, that's not so bad. That would be 255 over 100, which is 2.55. Okay. Yes?
In the last equation there, why is it minus 5?
Why is it where?
Where? In the last equation when we solved for x equals 7/10, why is it minus 5?
Why is where minus 5? Why is this minus 5? I don't know. Let's see, what do we have? Plus 4, plus 3, minus 2. Oh, that'd be plus 5. But the good news is it won't change anything else. All right, good, because it doesn't affect any of the computations we've done. And it doesn't affect the derivative. So now we scan our list. And we say, well, what are we looking for? We're looking for the largest and smallest on numbers. What's the largest number on our list? 11. So 11 is the absolute max. Now, which one's the smallest number?
1.
So 2.5 looks pretty good because it beats 2.75 and it definitely beats 2.55, even though they're pretty close, which is not surprising because these points are close together. So it's not surprising that the values are close together. But 2.5 is the smaller one. So this is the absolute min. And there you go. See, these problems aren't so bad. It's just be patient. Work the problems. Work the problems. And have faith that we'll pick better things than 7/10, 13/10. All right. Any questions on this problem or this type of problem? Good. All right. So now on to today's real topic. Optimization. Well, we've been doing optimization. Well, this is a different kind of optimization. Namely, we're going to look at optimization with a constraint. So, we want to say, I want to find the optimized value for f of xy. In other words, I'm looking for the maximum or minimum value of f of xy. And there's a constraint. G of xy equals c. So we've kind of done these problems. In fact, we did problems like this way back a year ago when we were in Calculus 1. We said, hey, we're trying to maximize or minimize something, and there's a constraint involved. Okay, so how did we do it back then? We said, oh, well, we'll just solve for a variable and substitute it in. And so we reduced it down to a one variable. Well, we can't do that all the time. So how do we do it in general? Well, here's sort of the idea. When we think of g of xy equals c, that's our constraint, it corresponds to a curve. So there's some curve. We're saying that look at the function along this curve. We want to say, well, what's true? And what we say is, okay, suppose I'm at a point. So I'm going to look at a point here. And remember, this is the curve. This part, this is my g of xy equals c. And just for a second here, let's suppose I were to draw the gradient. And let's say we're to go in that way. So here is our gradient of f at that point. Because remember, the gradient vector, it's a vector. So I can talk about what's the gradient vector at a point and draw it in. Now my question is this point going to be an optimum value? Is it going to be a potential max or min? So, what do we think? Well, the question is, if it's a max or min, we should look at, say, what would happen if I move just a little bit to either side? Because there's a really simple philosophy when it comes to saying I'm at a max or min. The philosophy says if I'm at a max or min, it's not to my advantage to move. Because I've already optimized my situation. So if I'm ever at a place where it's my advantage to move, I'm definitely not at a max or a min. Okay, so how do I know? Well, what we can do is we can say, well, what's happening to the function if we move in this direction? So we can look and say, suppose I move in that direction or I move in that direction. All right. So here we go. Look at this angle here. What can you tell me about this angle theta? Based on this picture. What? It's an acute angle. That's right. It's acute. It's a small angle. And you're probably thinking, meh. But what's the nice thing about that? Remember, what can we do with the gradient vector? What's one of our big tools that we can do with our gradient vector? It rhymes with directional derivative. Yeah, directional derivative. Very good. Okay, you cracked that code. So gradient vectors give us directional derivatives. They're saying, how is your function changing in a particular direction? So if I want to ask the question, how much am I changing? What's my rate of change in that direction? What I look at is I look at the gradient of f dot u. But because of the way that dot product works, this is really the magnitude of the gradient of f times that cosine of the angle. When this angle is acute, what's true about the cosine of the angle? It's positive. Which means that moving this way, my function f is increasing in that direction. So if my function is increasing, that says I should not stay put. I should move a little bit along the curve. What's happening in the other direction, on the other side? The function will be decreasing, because you can think about it here. Let's say this angle is alpha. This would be an obtuse angle. Cosine of an obtuse angle is negative. So on this side, f would be decreasing. So what happens is if I'm at a point and my gradient for f is not directly perpendicular. See, if we're perpendicular, cosine theta would be 0. There's no incentive to move. So what we want is we want a point that looks like this, where there's a nice right angle. Because if there's a right angle, I don't have an incentive to move. Because the directional derivatives say you're not going to change. When your directional derivative says you're going to change, you move. So that's what we have. So that tells us that our gradient has to be perpendicular to our level curve. So the gradient of f, this vector, has to be perpendicular. But there's also another thing that's perpendicular. The gradient of g is always perpendicular to g. That's one of the things that we proved about level curves. And that's how we got that when we were doing tangent planes to those surfaces, we said, hey, the gradient is the normal because it's perpendicular. So now I have that the gradient of f has to be perpendicular to the curve, and the gradient of g has to be perpendicular to the curve. So I have two vectors which are simultaneously both perpendicular at that point. What's the conclusion about the gradient of f and the gradient of g? Well, they don't have to be equal, but what do they have to do? They have to say have the same direction. We have a word for that. They have to be parallel. So, here's the fact. So we have that the following has to be true. The gradient of f is parallel to the gradient of g, which means that the gradient of f has to be some multiple of the gradient of g. And in addition to that being true, we actually have to be on the curve. Now what we get here is we get a nice system of equations. So this is a system of equations. Now you might say, how many equations are involved? Well, when our function has two variables, then the gradient of f equals lambda gradient g actually has two equations. Then this is another equation, and system of equations. Now you might say, yeah, but we've introduced a pesky thing called lambda. And that says, remember, two vectors are parallel if they're a multiple of each other. So now we've said, well, now we have to find another thing that we care about. But actually, here's the great secret. We don't really care about lambda. So that's going to give us an edge. We really care about the point. So here's what we do. When we have a question of this type, and the way to identify questions of this type is we say, okay, we have a constraint. We look for words like given that or such that, or it says optimize this function given that this function is true. Okay, so when we have a problem of this type, we set up our equations. And we have the following set. Gradient of f equals lambda gradient of g, and g equals our constant. So in other words, the constraint. We have the constraint plus this extra fact that our gradients have to be parallel. Now, we find all the points which solve this system of equations. And how do we do that? Well, this is something which I have found to be incredibly useful. And if you remember this, you'll get through about 95% of these problems. When in doubt, solve for lambda. And you probably think, but that's the last thing we need to solve. We don't need lambda. Exactly. Exactly. That's why you solve for it. We'll show what we mean by that in a second. So once you've found your points, now what you've done is you've essentially gone back to our make a list philosophy. So we're making a list of all our points where these things are satisfied. And finally, what we do is we plug these points into our function and interpret the results. So once you get the flow of these questions, they're actually very quick. Set up the system of equations, solve for your points, plug them in. So let's do some problems. Find the maximum and minimum values for f of x, y, and I can already see there's a typo here, not given 1/4 x squared plus y squared equals 1. So, let's just sort of identify things. This is what we're trying to optimize. This is our constraint. And the sort of the key that's the constraint is we have an equation, 1/4 x squared plus y squared equals 1. So we can write this as a value. So we're going to think of this part right here. This is our g of xy. So g of xy equals some number. So 1/4 x squared plus y squared. So how do we proceed? Well, we take our gradient. So we have the gradient of f. That would be negative 2x, comma, 2y. And then we have our gradient of g, which would be 1/2 x, comma, 2y. And we say that gradient of f equals lambda gradient of g. Well, all right, becomes, you do it entry-wise, minus 2x has to equal lambda times 1/2 x, and then we have that 2y has to equal lambda times 2y. All right. Well, let's just pick an equation. Let's suppose we pick this bottom equation. 2y equals lambda 2y. What has to be true? Sorry, what? Is it true that lambda has to equal 1? That's certainly possible. Is that the only thing that could happen? Y could be 0. So be careful, because a lot of people would see this, oh, 2y equals lambda 2y, divide both sides by 2y, lambda equals 1. But what's the problem with that? Well, the problem is when you divide and you cancel, the problem is, what if you divide by with 0? So you should never divide unless what you're dividing by, your positive is not 0, or you don't cancel anything. Now, another way you could have gone to this is you could say, look, I can definitely divide by the 2's, because those aren't 0. Then I can move things across. So this could be written as lambda y minus y equals 0, and then I could factor out y times lambda minus 1 equals 0. So you can get that y equals 0 or lambda equals 1. So let's suppose lambda equals 1. Then in the first equation we get minus 2x is equal to 1/2 x. Well, what x is it true that if I multiply it by negative 2 is the same as if I multiply it by half? It would correspond to x equals 0. Now, that's the x coordinate. How do I find the y coordinate? Well, the answer is I also have this other equation, the constraint. So if x equals 0, I come back and plug into the constraint, y squared equals 1. So we get y is plus minus 1, which means we get the points 0, 1, and 0, negative 1. Now, how about y equals 0? Well, if y equals 0, now I know what y is. Again, I can go right back to my constraint. That says that 1/4 x squared has to equal 1, or x squared has to equal 4. So what is x? Plus or minus 2. All right. So what does that give us? Well, it gives us the points 2, 0, and negative 2, 0. So we have a list of points. So the points where a max or min could occur is at 0, 1, 0, negative 1, 2, 0, and negative 2, 0. So the next thing is we plug them in to our function. So we plug in 0, 1. What's our value that we get out? Well, it'll be 1 squared minus 0 squared, which is 1. Plug in 0, negative 1. Negative 1 squared minus 0 squared is 1. Plug in 2, 0, 0 squared minus 2 squared, negative 4. Negative 2, 0, 0 squared minus negative 2 squared, still negative 4. And we interpret, well, which number is the largest? The 1. So this is the max. Which number is the smallest? Negative 4. That one's the min. All right? So that's the process. This is one where we didn't solve for lambda, but just a warm-up, Okay. Now, are you confident about this answer? 1 and negative 4. Yeah, you do. Okay, all right. We'll come back and ask if you're confident in a second. Warning. Be careful on how to interpret the results. So the following is actually from a final exam from 2011. Maximize 1 over x plus 1 over y, subject to x plus 4y equals 1. So, what's our function? Yeah, the part that we're trying to maximize, that's our function. So this is our f of x, y. So that's what we're trying to optimize. What's our constraint? Yeah, the x plus 4y equals 1. So this right here, that's our function g of x, y, which is x plus 4y, which is equal to 1. So, we do what we do in these problems. When we have a problem where we have a optimized with the constraint, gradient of f equals lambda gradient g, which you can write as f sub x equals lambda g sub x, and f sub y equals lambda g sub y. Well, what is f sub x? Take the derivative of this function with respect to x. What do we end up with? Negative 1 over x squared is equal to lambda. What is g sub x? 1. Okay, f sub y? Negative minus 1 over y squared equals lambda times 4. All right. Well, we can't have x and y be 0 because that's just undefined. So we're not going to worry too much. But notice what we can do is we can actually say, hey, I can say that minus 1 over x squared is equal to lambda. This is 4 lambda, so we can say that minus 4 over x squared is 4 lambda, which is also the same as minus 1 over y squared. So what we can do is we can use the connections about lambdas to get a connection between x's and y's. So, if we go further, minus 4 over x squared equals minus 1 over y squared. The minuses on both sides cancel out. 4y squared equals x squared. So what does that tell us about x in relationship to y? Well, let's take the square root of both sides. What do we get? X equals 2y. Or x equals negative 2y. Now we have two possibilities. So if we do the x equals 2y possibility, what do we get? Well, come to your constraint. 2y plus 4y equals 1. So 6y equals 1. So what is y? 1/6. So then we have x is twice that. So we get x is twice 1 over 6, so it's just 1 over 3. And then y is 1 over 6. If we go to x equals minus 2y, so then we get minus 2y plus 4y equals 1, which says that 2y has to equal 1. So what is y? Y is a half. So that gives us a point, 1/2. Then negative 2 times a half is negative 1. So these are the 2 points that come out of the process. So these are the 2 places where the gradient is parallel in both the gradient vectors. So the gradient of f is parallel to the gradient of g. Now, let's look at the results. We're going to plug both of these functions in. 1/3, 1/6, and f of minus 1, 1/2. When we plug in 1 over 3, 1 over 6, well, if we flip 1 over 3, we get 3. And if we flip 1 over 6, we get 6, which means we get 9. If we flip 1 over minus 1, we get minus 1. And if you flip 1 over 2, you get 2. So you get 1. Now, I have written the question to maximize this. Which one of these two is the maximum? We want to say 9, right? 9 feels very maximy. It's like 9 is bigger than 1. You can't fool me, Steve. You fooled me before, but not this time. I'm a pro at this. Okay. It turns out that this point 9, this is actually a minimum. And this point 1 is actually a maximum. Nobody caught it when they took the exam. None of the professors caught it. Now you might say, I don't believe you, Steve, because I know 9 is bigger than 1. What do I mean by saying 9 is a minimum and 1 is a maximum? Well, it turns out that this is sort of a curious case. So if you graph where this curve is at, it's a curve that comes something like this. So here's our constraint. Now, the issue with this particular function is, notice it's not defined at these 2 points because you have a 1 over a 0 involved. Either x equals 0 or y equals 0. Now, this point where you had 9 was here. Now just imagine you move in one of these directions. Well, what happens is you're going to be moving to a point where you have a 1 over a tiny number. So what's going to happen to the function along as we move in those directions? The answer is the function blows up. It gets big. So if you were to draw the three-dimensional picture, it's going up this way, it's going up that way. So 9 is actually where there's a minimum of the function. On the other hand, if you came over to this point, which is this place where you get the 1, if you go that way, what will happen is, because you're going to get a 1 over x, but x is negative, it's actually heading towards negative infinity, so it's going down. And if you head off that way, x and y are getting big, and so it's heading to 0, which means that this point is a max. So that 1 is located where there's a max, and 9 is located where there's a min to the function. Now, I will tell you, everybody who circled 9 on the test got full credit, because nobody caught it. Now, that's partially because of the story of the fall 2011 final exam. It's a dark story that we don't like to talk about very often, but I'll tell you a little bit about it, because I have a minute or two. That was back when they had really nice graduate students, and one of the graduate students was like, I'm going to be so nice, I'm going to give my students a practice exam where their practice exam is the real exam where I just changed the numbers. And we found out that this had happened about 3 hours before the exam. And so with 3 hours to go, we wrote a new exam, so we didn't actually check the problems. And this was on there. So yeah, you have to be careful. So here's the punchline for this whole discussion. The reason I'm bringing this up is, when you find these critical points, we're not testing whether in fact they are maximum or minimum. We're just saying, here's a good point. You should look at this point. So now let's go back to the previous question and then say, okay, are we confident that these are max and mins? Now, how do you answer that question? There's 2 ways to do it. Now, in this particular case, we get a freebie. If you sketch the curve 1/4 x squared plus y squared equals 1, what's the curve look like? It's almost like a circle. What is it? It's an ellipse. So it's a little bit wider in the x direction than it is in the y direction. Well, it's not just that it's continuous, it's that it's bounded. It's a closed, bounded curve, and the function is not blowing up anywhere. So if you have closed and bounded and a nice function, you're guaranteed to have an absolute max and absolute min. That was one of our results that we've talked about. And so because we have a nice function on a nice curve, we're guaranteed to have a max and min. So you don't have to do anything at all. But if you were still paranoid, then what do? Well, the answer is, you say, look, these were the points I found. And if you have to, if you were in a pinch, what you do is just say, just move a little bit and say what happens near the points you're interested in. Because if I know what's happening near the point I'm interested in, then that can tell me if I'm at a max or a min. So that's what you do if you're in a pinch. But I will say that we never actually ask you to prove it's a max or a min. Now you might think that, wow, we've learned our lesson. We'll never do this again. Well, it turns out, in the spring of 2019 final exam, we also had a question that asked for find the maximum. And there was an answer. It's like similar to like what this was, that people wrote down 9, and they felt pretty good about it when the answer was infinity. But, you know, one of these days we'll get it right. Okay, all right. Okay, all right. Serious stuff. Here we go. Find the points which are nearest and furthest from the origin, given 7x squared plus 3xy plus 3y squared equals 25. All right, this is a really good one. This is the kind of problem that this was tailor-made for. All right, so how do we do this problem? Well, first off, where's our optimization? Where's our f of xy? What we're trying to optimize. Is it this? See, this is not our thing we're optimizing. This is our constraint. So there's nothing here. Well, there's not an equation. There's a descriptor. So this is a fun thing where we get to create the equation. All right. So what's our equation? Well, someone has seen it. See, we want to be nearest and furthest. So whatever is it we're measuring? Distance. So the distance is what we're trying to optimize, and that's the square root of x squared plus y squared. And now we're saying, okay, so that's what we have to optimize. But, we see that there's a square root involved. Now, one of our goals in life is to get rid of square roots. So, what are we going to do? Well, the answer is, we're going to get rid of the square root. And just say, let's optimize x squared plus y squared. It might feel like we're cheating. And it's not. It's like we're being insightful. So what can we do? Well, if you're trying to optimize the square root of a function, what you're really saying is, I want to optimize what's inside the square root. Because the larger the inside is, inside of a square root, the larger the value. And the smaller the inside is, the smaller the value. So I can optimize the inside. So this is what we're trying to optimize given this constraint. So here we go. Gradient of f equals lambda gradient g. So again, we get f sub x has to equal lambda g sub x, f sub y has to equal lambda g sub y. What is f sub x? 2x. What is g sub x? Well, 14x plus 3y, and that doesn't have anything. F sub y, 2y, has to equal lambda g sub y, which is 3x, 6y. All right. So now we look at this and say, we got to solve all points x and y which satisfy this. Okay. I'm starting to feel doubt. Well, when in doubt, what should we do? Solve for lambda. So here's the solve for lambda in its true form. So I'm going to solve for lambda in this first equation, and I'm going to get that lambda is 2x over 14x plus 3y. But I could have solved for lambda in the second. That would be 2y over 3x plus 6y. Now, lo and behold, we have a nice relationship. So it has to be the case that 2x divided by 14x plus 3y has to equal 2y divided by 3x plus 6y. So we can start from that point. Now, what's the next thing we do? Cross multiply. Because fractions are not our friends. They pretend like they are, but they're not. So we get 2x times 3x plus 6y is equal to 2y times 14x plus 3y. Okay, well, what comes next? All right, well, certainly we can cancel off some 2's. And if we distribute, we'll get 3x squared plus 6xy is equal to 14xy plus 3y squared. So we'll move everything to one side. 3x squared minus 8xy minus 3y squared equals 0. So what's going to happen when you do these types of problems is you're going to say gradient of f equals lambda gradient g is going to produce a new equation. It's a new equation that relates x and y. And the reason that this is good is you now have two equations, namely the gradient of f equals lambda gradient of g and your original constraint. Two equations and two unknowns that we need to solve. Now let's look at this expression, 3x squared minus 8xy minus 3y squared. What would we like to be true? Take a second to factor everything that you've learned into your answer. What would you like to be true? It would be wonderful if it factored. We'd be like, wow, that's amazing. What do you think? Will it factor? I'm going to go on faith that the people who wrote these problems are people who like us. Let's try and factor this. Any guesses? Well, there's probably going to be a 3x and an x. That's a pretty good guess. And now we have to say, well, look, there's a 3y and a y. We can't have the 3x go with the 3y. Because if the 3x went with the 3y, then everything would have to be a multiple of 3. So that says the 3y would have to go here. So if it factored, it would have to look like that. Now the question is, what are the signs? 3x plus y, x minus 3y. Now we check. 3x squared, that's good. Minus 9xy plus xy, that's minus 8xy. Minus 3y squared, that's great. It works. That's the right factorization. So we can conclude that either x equals 3y or y equals negative 3x. So now we have to look through those two possibilities. Remember, we have this second equation. Which one do you want to tackle first? X equals 3y. All right. X equals 3y. So come into your constraint. Everywhere you see an x, put 3y. So we're going to get 7 times 3y quantity squared will be 9y squared. Plus 3 times 3y times y plus 3y squared equals 25. Now if you look at this, you get 63y squared plus 9y squared plus 3y squared, which is 75y squared. Has to equal 25. Or y squared equals 1/3. So what is y? Plus or minus 1 over the square root of 3. What is x? Well, x is 3 times that. So what we get is we get the following points. So if we have 1 over square root of 3 is the y, 3 times that will be square root of 3. If we have minus 1 over square root of 3, 3 times that is negative square root of 3. Because if I can think of 3 as square root of 3 times square root of 3. So square root of 3 times square root of 3 times a 1 over square root of 3. One of the square root of 3's cancel. So those are points. Now, that's if that's if we did x equals 3y. What would happen if we did y equals minus 3x? Well, similar process. Everywhere I see a y, I'm going to put a minus 3x. So 7x squared, that's fine, plus 3x times minus 3x plus 3 times minus 3x quantity squared equals 25. Well, this is 7x squared minus 9x squared, and then it'll be plus 27x squared equals 25. Nice thing is these are all x squareds. 7 minus 9 is negative 2. Plus 27 is 25. 25x squared equals 25. So what is x squared? 1. And what is x? Plus minus 1. Which means that we get x is 1, or negative 1. And remember, y is negative 3 times that. So we get negative 3 and positive 3 respectively. So these are the 4 points that come out where the gradient of f equals lambda gradient of g. Now, what do we do next? Well, we plug each one of these into our function. Well, it's the function x squared plus y squared. So, if we plug this in, we're going to get 3 plus 1/3, which, I'm running out of space, but 3 plus 1/3 is 10/3. 9/3 plus 1/3. Here we'll get 3 plus 1/3, which again is 10/3. Here we'll get 1 plus 9, which is 10. And here we'll get 1 plus 9, which is 10. Now remember, our answer is the points. So the nearest points are the ones where we're smallest. So that's square root of 3, 1 over square root of 3, and minus square root of 3, minus 1 over square root of 3. The furthest points would be 1, negative 3, and negative 1, 3. And that would be the answer. On a side note, it's not so clear what this is, but suppose you were to guess. 7x squared plus 3xy plus 3y squared equals 25. If you had to guess, what would you think that was? It is an ellipse. Certainly if there was no 3xy there, you'd say ellipse. The 3xy, what that does is it tilts the ellipse. And so the effect that ends up happening is an ellipse that kind of looks like this. And so what we've done is we've found that there were the furthest points, and then there were the nearest points. So it's finding the nearest and furthest points on a tilted ellipse is what this problem becomes. All right, well, let's quickly do one more, because we have to be quick. For xy greater than or equal to 0, so in other words, we are constrained. We're going to definitely stop there. We're definitely going to stop there. Find the optimum of 3xy minus 5y, given that 4x plus 3y plus xy equals 30. So here's our f of x comma y. This is our g of x comma y. Now we go through our process. F sub x equals lambda g sub x. F sub y equals lambda g sub y. By the way, our process works if we have functions of 3 variables as well. It's the exact same process. If there was a third variable, we'd say fz equals lambda g sub z. It's just a system of equations. Always remember, solving for lambda, that will make things pretty easy. So here we'll get 3y has to equal lambda times, well, 4 plus y. Then we're going to get 3x minus 5, there's a minus, has to equal lambda, and then over here, 3 plus x. So solving for lambda, because I'm in doubt, and it works pretty well, that equals lambda, but it also 3x minus 5 over 3 plus x. Cross multiply, 3y times 3 plus x has to equal 3x minus 5 times 4 plus y. Now what? Well, expand. 9y plus 3xy equals 12x plus 3xy minus 20 minus 5y. Now, it's not looking too promising until you say, oh, wait a second. The least nice term cancels. So you should expect things to happen. Things will cancel, things will factor, beautiful math will occur. All right, move things around. We can say that 14y is equal to 12x minus 20. Okay, so that's a new relationship that we have. 14y equals 12x minus 20. Now, what else do we have? Well, remember we also said that 4x plus 3y plus xy equals 30. What can we do? Well, what can we do? Good questions. This is one of those things that it's supposed to just pop out at you and say, aha, here it is. Okay, but it's not doing that, you silly problem. All right, well, there's always the brute force way, right? Okay, what's easier to solve for? Solving for x or solving for y? Okay, so 7y plus 10 equals 6x. I'm just going to divide everything by 2. And now, throw that in up here. Okay, so how do we throw that in? Well, if I multiply everything by 6, that'll make it a little bit easier. 24x plus 18y plus 6xy equals 180. So multiplying everything by 6. So we're going to get 6x, so that's 4, times 7y plus 10, plus 18y, plus 6x is 7y plus 10, times y equals 180. Okay, 28y plus 40 plus 18y plus 7y squared plus 10y equals 180. And now I'm wondering if I should have started this example. Well, you often wonder those things when you start. 56y, and then it'll be minus 140 equals 0. Divide everything by 7. Y squared plus 8y minus 20 equals 0. And you say, does that factor? Then you say, come on, this is calculus. Everything factors. And factors as y plus 10 times y minus 2. So you get y equals negative 10 or y equals 2. Well, one of these things we don't care about. Which one don't we care about? The negative 10 we can drop because that's not part of our region. So we know we're looking for a place where y equals 2. Well, if y equals 2, then 7 times 2 plus 10 equals 6 times x, or 24 equals 6x, which says x equals 4, which says we are at the point 2, 4. So this is 4, 2. Yeah, thank you. So that's where it happens. So the optimum is f of 4, 2, which would be 3 times 4 times 2. That would be 24 minus 5 times 2, which is 10, which is 14. All right. And so that's what it is. That's the optimum. And if you want to say, is it a max or a min, go to the corners, and that'll tell you. But I'll leave that as an exercise for you because we're done.